if you find the blue one to be a little bit wider. Okay? So if the red one normally would go over 1 up 1, the blue one goes over 1 up a half, then over 1 up 3 halves. Or you could just do a table of values and get some points and find out that this one's a little bit wider. The green one would go over 1 up 2, then over 1 up 6, and would be narrower than our original red one. Now we just learned what negatives do earlier. So if the blue graph is 0.5x squared, if I put a negative out in front, that negative is outside, that will take that blue graph and flip it down. So my purple graph is just the blue graph. And same thing with my orange graph, that would just be my green graph. Flip it down. But now we're going to take the language that we did for grade 11. Because in grade 11, we were just worried about parabolas, so making something narrower or wider made sense. But those words won't work as well when we get to what we want to say in grade 12. So first of all, I want you to notice that all of these numbers are outside. Outside is vertical. Outside always affects y values. So I'm going to take a point on my original graph. I'm going to take the point 2, 4. Also, some things we notice with our y values, like when things moved up and down, is it exactly as you saw and as you thought. So notice here, when I have a half, something's going to happen to my y value, and sure enough, my y value got cut in half on the blue graph and has 2, 2. And on the green graph, I have a 2 out in front, and sure enough, my y value gets multiplied by 2, and I now have 2, 8. And instead of saying that the blue graph is wider, we are going to say it has been vertically compressed. If you took your red graph and imagined there was a floor at the x-axis and you squished it down towards the x-axis, that would make it wider. But we'll say it's been vertically compressed. The reason we have to change our language is because wider kind of makes you think you're doing something horizontally. But in this section, we're actually doing something vertically. And same thing, the green one, we imagine we took the red graph and stretched it away from the x-axis. It's like it's wherever there's x-intercept, it's glued on, and then you grabbed onto it and stretched it up, and you would get the green one. And then you could also add the reflections in there as well. So we're going to find any number on the outside that either stretches it or compresses it vertically. So when we go to example 1, here's the graph of f of x. Sketch the graph of y equals negative 1/4 f of x. And you're going to notice that we're going to start labeling things because we're going to get all of our transformations will eventually be put together. Moving left, right, up, down, flipping, stretching horizontally, compressing vertically, all going to get combined. So one of the things that we're going to do is we're going to start labeling things that we see. I see a negative and a 1/4, and I see that they're both outside of the function. So I'm going to use V for vertical, and the negative R for reflection. So that negative is a vertical reflection. The 1/4, and maybe I'll put this in brackets because it's the first time we're using this letter. Is going to be a vertical compression.
V is what?
V is for vertical. Vertical reflection.
Hi, could I please have Celia to the office? She'll be leaving now.
Okay,
Thank you.
so I'll put the rest of the stuff on the videos and you can catch up that way. So what we would say algebraically, we can actually put these two together. Because the vertical reflection, we learned that multiplies our y values by -1. The vertical compression, we're going to multiply our y values by 1/4. So if I'm multiplying by -1 and I'm multiplying by 1/4, I can put those together and say I'm going to multiply all my y values by 1/4. And as we do more complicated transformations, we're going to start taking points from our original graph and then doing the math and seeing where did they end up. Now, on my original graph, first of all, this is the most important point. 0, 0. On this graph, that's where things change. You definitely want to know what happens at that point. Now, I could pick any other points on this graph that I want. But sometimes for mental math purposes, we try to choose ones that'll work nice. What do I want to do? I'm going to want to multiply all my y values by -1/4. So I might choose this point, 4, 4. Or I might want to choose this point, -8, 8. Because the y values easily multiply by 1/4. It would not be wrong to choose other points and have fractions, but this might just be a little bit easier. Then to show, what I like to do to show work is I like to say, well, these points are going to change. They're going to change because I need to multiply my y values all by -1/4. So what do they change to? Well, since I'm only changing y values, my x's are all going to stay the same as they were. So 0, 4, and -8, those aren't going to change. When I multiply y by -1/4, well, the first one's a 0, so that's easy, stays 0. But here I have 4 multiplied by -1/4 will be a -1. And then my 8 multiplied by -1/4 will be -2. And now if we plot these points, we'll be able to draw the graph. Okay? Now I would get you to plot the points, but then many of you would make a little mistake. 0, 0, I'm pretty sure you guys would be okay with that. But should I make the mistake? And then, sure, just don't write it down. Here we go. Here's 4, -1. Did anybody else make that mistake? No, you can't. I led you into thinking more. Why is that wrong?
Because it's not 1 pixel equals 1 thing.
Yeah, it's going by 2's again, right? So this one.
What?
I know. Did you make the mistake?
Yes.
And then -8 and -2 would actually be there. Then one thing that is useful after you've got your graph is check, do we have a vertical reflection? Yes. Has it been compressed towards the x-axis? Yes. So it appears that things are correct. Except for that you gotta be careful with those points, because they could say, oh, state domain and range of each function, of course. So the original ones, domain is everything. The range is y is bigger than or equal to 0. And on our new graph, the domain is still everything, but the range is now less than or equal to 0. Now, when the textbook or exam gives you a question like this, with the graph, it's a little bit easier. But this question could have been asked, and I'll write the same question without the domain and range. I'll take that sentence out. But I'll show you a different way this question could be asked just so that you can see. Here's the same example. Sketch y equals -1/4 absolute value of x. Do you see that that's the same question that we were asked? The difference is here you have to recognize the absolute value of x and say, hey, that's that red graph. And you have to draw the original graph on your own. And then notice there's a negative and a 1/4 outside of that original graph. That would affect your y values, vertical reflection, vertical compression. This is a lot shorter to write, but now you have more work because you have to recognize the original graph from our colored papers, and then you have to know how to work with that and change that original graph. Okay, questions for practice on this one? Just number 3.